Hello students, and I'm back with another lecture. And this lecture will cover the last topic of our course, which is bioreactors, alright, or bioreactors in tissue engineering. So, this particular topic, um, that is bioreactors, you must have studied in a biotech course where I'm pretty sure you have done the course is bioreactor design and analysis. So there the people are using the bioreactors for bioprocess engineering, where some particular biotech product like enzyme and antibodies, antibiotics, vaccines, etc., that are made at a very large scale. All right. But here for tissue engineering, people use different kind of bioreactors. So that don't confuse in between these two types. So, the general definition of what a bioreactor is, and it is applicable for both the fields, is it's a device that is used to carry out all biological or any biochemical process under controlled environment, like there will be control of pH, temperature, pressure, and also the continuous supply of nutrients is there with continuous waste removal. All right. So this is the definition. Now, for tissue engineering, why we are interested in using bioreactors? Because use of bioreactors gives us the following advantages, and uh, whether or not to use it depends on your application, and it can become a very good solution to a problem. Say you are not able to have the required number of cells, which is going to create the clinical advantage or which is going to give you a clinical advantage. So you need very large number of cells. Okay. So then you can use bioreactor. And for other examples, like for better maturation of your tissue, for better media and nutrient transport. So it's the same thing is written here. Establish spatially uniform cell distribution on 3D scaffold. So this goal can be achieved when you use a bioreactor. Then you can also maintain desired nutrient and gas concentration in the medium. You will be able to efficiently, or you will be able to get very good mass transport. That is, cell transport as well as the media content. So that is mass transport will happen very nicely or very efficiently. And lastly, you will be able to expose your developing tissue to some physical stimuli, and that will ultimately help in maturation of the tissue with better characteristics. So, when we talk about spatially uniform cell distribution, so tissue engineering, we require that the porous 3D scaffold it should develop along with cells and the growth factors, and ultimately it will create a 3D tissue structure, right? But the challenge is the cell cell density. Means we require very high cell density initially in order to make sure that the final tissue construct has like equally say two order of magnitude. For example, two order of magnitude higher cell number because ultimately the cell is going to proliferate, right? And the cell number is going to increase. But that is what we expect. In reality, something else happens. Initially, we usually begin with the cell numbers which are quite small. And as the cells proliferate and increase in number, the cells which are there at the center of the scaffold, they starts to die. Okay, when we culture these kind of scaffolds and normal cell culture techniques, like that is the static culture. Whereas this problem can be solved if we use a bioreactor. So how? So let's go through the rest of the points. So initial distribution of the cell, it can play a very important role on how the tissue will mature. So the first and foremost work for for any tissue engineer is to seed the cells homogeneously with a high density and ensure that the cell is uniformly distributed. Then only they will be able to that he will be or she will be able to ensure that the tissue develops in a uniform manner. Now, there are various strategies available to date to seed the cells. You can use static seeding, which is the normal cell culture technique uh, that we do routinely. Okay. Then there is dynamic cell seeding and there is magnetic cell seeding. I'm not interested to go and discuss about magnetic cell seeding, but to this current topic, the knowledge of static cell seeding and the dynamic cell seeding is important for us. Static cell seeding is very simple and mostly used. Here, what we do, we prepare a scaffold, a 3D scaffold through any of the fabrication techniques we already know. And on top of it, using our pipette, we dropwise add the cell suspension, okay, and create like a very thin film of cells and the media on top of it. And then allow the scaffold to become submerged in some higher volume of media and give it time to grow, give the cells time to grow. So what we expect, say after 48 hours or 72 hours, the cells will migrate through the pores of the scaffold and distribute themselves within the bulk of the scaffold. Okay. So that is how static seeding works, and this is the expectation from that. But this particular technique has a very low efficiency. Means it say you have taken or you have decided to seed 1 is raised to the power 10 to the power 6 cells. It is 1 million cells you decided to seed. And when you are adding drop-wise your cell suspension, okay, that is containing that many number of cells, it is possible that few of the cells, since they are in suspension form, right, they can easily slip off the scaffold and fall on the, say you're working on a glass petri dish, so it can fall on that rather than staying adhered onto the scaffold. So that basically leads to loss of cells, and which is why I have said that, or it is written here that the seeding efficiency is poor. And also, depending on how porous your scaffold is, it will decide how well your cells will be able to infiltrate inside that. Now, this particular problem, that is seeding efficiency is low, it can be solved if we use dynamic cell seeding using bioreactors. So we can actually improve the seeding efficiency up to 90%. That's quite high. So in bioreactors or for dynamic cell seeding, the general principle is like as the cells are like added onto the scaffold, okay, and as they are added, they are in an they are exposed to such an environment that if some cells get lost due to like not being able to adhere well and remain in suspension, they can again be circled back, okay, and onto the scaffold. So the scaffold is placed in that media in such a way that it is always in contact with the cell suspension around it, and the cells can easily come or say like through shaking or simple rotating, something like that. We are applying some continuous force, gentle force that allows physical contact of the suspended cells and the scaffold. And in this way, we can ensure that the cells are physically kind of manipulated to go inside the scaffold. Hence, the seeding requirement. So, if we use dynamic cell seeding, we can actually meet the seeding requirements for tissue engineering application. So, what we do for tissue engineers, what is important for us, or what are the seeding requirements that is important for us, is that we should be able to maximize the utilization of the cells that we are using. So, if we are working with primary cells that are taken from a human, right? So the source of the cell is like limited. We cannot really uh, like get those cells again, right? So we have to utilize the amount of cells completely. We cannot waste or we cannot risk loss of that cell. Next, we should be able to make sure that the cells don't remain in suspension for a very long time, and the flow of the media, it should be happening at such a rate that it is allowing the suspended cells to come in contact with the scaffold very quickly. And lastly, tissue engineers always want that the cells should be homogeneously distributed all over the scaffold. All right, and that will ultimately help in smooth and easy progression of tissue maturation process to happen. And all these requirements can be fulfilled if we use bioreactor and do dynamic cell seeding. And the next goal of using bioreactor is to make sure that the desired amount of nutrients and the gathered oxygen concentrations are maintained at all times. Okay, so that is the challenge basically. If we do static culture, we are relying on the fact that the operator will change the media once a day or twice a day, depending on how much cells he or she has used. So it's like a batch reactor, means everything is put together. Okay, reaction happens, and then after some time, it is removed, right? Waste is removed. So static culture, we do that only. After 48 or 24 hours, we change the media, and then again next 48 hours, we change the media. So but the utilization of the media is happening gradually, right? Over that 48 hours. And the amount of nutrient is that is being depleted, say in between the two media change periods, is not replenished. And the cell number is going to like increase that too in real time. We cannot like say with surety and only after 48 hours cells will consume the nutrients. You get the point? The continuous removal of waste and continuous supply of nutrients will make sure that the cells are always in proliferative condition, means at the exponential phase. That again will help in reaching higher cell density. Okay, so that is the idea of using idea behind using bioreactors to achieve this particular goal. So this is one thing. You should keep this in mind, and I'll quickly go through the rest of the points. In static culture, the only way by which the nutrients in the media can reach the cells or the waste produced by the cells can be removed means that transport of these types of masses, it happens only through diffusion, and that to passive diffusion. Okay, but the diffusion process is not a very what do you say? It cannot ensure very long uh, distances. Means the mass that is getting diffused, it cannot travel very long distances. It will only Diffusion will only happen when a concentration gradient is created. So at the center of the scaffold, if the nutrient or the waste is saturated, means there is no concentration gradient, and even in the outside of the scaffold, it is saturated. Means the concentration of the waste or the concentration of the nutrient is equal at the center as well as the outside, then the diffusion process will not happen. So, due to this limitation, uh, the scaffold or the cells in the scaffold, they will either continue to stay in a environment containing the waste products, or it will have too much of nutrients at some time. Okay, and uh, like very less amount of nutrients as well. That is also possible. So diffusion process is not beneficial in these kind of cases. It becomes a limitation actually. Also, as the culture time increases, right? So if you're planning to culture for say 21 days or 30 days, so it's a very long time, no? The cells that are there, they will also be active, or you'll be creating conditions that keeps them alive. So during this particular time period, the cells will grow in number. They will also secrete the ECM components, and when they do that, the ECM they will deposit on the scaffold. So the scaffold inner pore, onto the pore walls inside the scaffold. So that will ultimately reduce the size of the pores, and that again will decrease the rate of diffusion of, say, nutrients or the rate of diffusion of the waste or the oxygen, etc. Okay, so diffusion is not the answer when you are working with large scale scaffold and when you are going to culture your scaffold will for a very long period of time. And then we have to ultimately look for dynamic culture, dynamic culture conditions using bioreactor. The last very useful aspect of using bioreactor is we can expose the developing tissue to a physical stimuli. So why this is important? So people have actually reported that, say, mechanical force, tensile or compressive forces, these forces can actually improve the activity of 3D scaffold, and hence their in vitro progression is how they matures in vitro. People have found that if we give a cyclical mechanical stretch, means after every few seconds you're stretching the scaffold, and that scaffold say is seeded with human heart cells. So here heart cells are only written, what particular population is not mentioned, all right? So the cell scaffold that is seeded with this human heart cell and it is exposed to oscillatory mechanical stretching forces, then people have seen that these heart cells they proliferate better. Okay. Similarly, a collagen-based scaffold, which is having some muscle cells, and that is when exposed to again like similar type of stretching forces, then people saw that the cells they express more the elastin fibers and tissue organize this kind of again mechanical stretching it also helps in better organization of the cell, that is smooth muscle cells inside the scaffold. So this example, this point, what I'm trying to say is a physical stimuli, simple physical stimuli like stretching, uniaxial stretching cell. It has been used to show that in presence of this particular stimuli, when it is cyclically given to the scaffold containing the cell, uh, the cells respond better, they grow better. Okay, they enhance their synthesis capacity becomes enhanced because we are trying to again the goal of tissue engineers is to mimic the cellular microenvironment, induce cellular microenvironment. So in native conditions, these cells do respond to this kind of physical stretching. No, so we are in vitro, we are doing that, and that is why we are getting good results. And also, people have seen that mechanical like stimulations, they can act as good signals, all right, for differentiation. Because people have seen with stem cells that when they are exposed to similar kind of mechanical stimulations like forces, like tensile or compressive forces, they will, or some signaling pathway gets activated in them, which triggers their differentiation to a particular type of phenotype. So we are not using any growth factors or receptor to direct the differentiation, rather using mechanical stimulations. Now I will discuss few of the bioreactor types which are being used in tissue engineering applications. So um, let me stop here and I'll continue from this in my next recording. Thank you.